Thank you so much for the introduction. I've actually been following this seminar all year long, and I am delighted to be able to speak here today. So I'm going to talk about threshold linear networks today, and I decided this is kind of a new talk, at least organizationally, because I'm going to focus on the theorems and then show you some hopefully cool applications of them. So let's see, let's get started. So the basic setup is hopefully familiar to most people in this audience. What we have is some simple ordinary differential equations that have a nonlinearity. So this is very important. The threshold nonlinearity with the brackets here is what makes everything interesting. Without that, this would actually be an honest to goodness linear system of ODEs, and it would have basically no nonlinear dynamics. I just want to point out there are two data point items that specify the threshold linear network, this W matrix and the vector B. And so we'll refer to a TLN with matrix W and vector B as just the ordered pair WB. And these networks, as many of you know, can exhibit all kinds of interesting nonlinear dynamics, including multi-stability, limit cycles, chaos, and quasi-periodic attractors. And moreover, all of these different kinds of dynamics actually emerge for effectively inhibitory W, where the entries of the W matrix are non-positive, and even for a constant external input vector B. So it's completely internally generated dynamics. So these networks have been used in neuroscience for a long time. I mean, I can make a long list of papers that apply them. The theory that first caught my eye was actually developed by Hanlesser, Sung, Slotine, and Shi 20 years ago now. And they actually proved some really lovely theorems about the symmetric case a long time ago. So one of the theorems they proved was an analog of the famous Hopfield model result, where they gave simple conditions that guarantee convergence of the network to a stable fixed point in the symmetric case. This caught my eye and Vladimir's when we were postdocs back in 2008, 2009. And together with Anna Degeratu, who is another mathematician, we wrote a couple of papers continuing on the symmetric case and proving more theorems about what sets of stable fixed points you could simultaneously encode in a network like this. And then I started working with Katie Morrison about 7 or 8 years ago. And this is one of our first papers on the subject, still completely in the symmetric case. But for purposes of today's talk, I'm going to focus on the non-symmetric case. So in the last 5 years or so, I have been, together with many collaborators, we have been really focused on trying to understand what happens when W is not a symmetric matrix. This is, of course, much more challenging, but in this case, you get this really interesting mix of stable and unstable fixed points. And it turns out that because of the piecewise linear nature of these systems, it's more mathematically tractable than one would initially believe, despite being high dimensional nonlinear dynamical systems. So the results for today's talk are all kind of for the general non-symmetric case. Of course, that includes symmetric matrices, but I want to emphasize that symmetry is never an assumption. And there's a bunch of openly accessible papers for that. So the motivating question we have is, what is the relationship between the attractors of the network and its underlying architecture? And we really want to understand this in terms of the pattern of connectivity as reflected in a directed connectivity graph. And by attractors, I mean not just stable fixed points. I mean limit cycles and other dynamic attractors, quasi-periodic, chaotic, what have you. So here are the 10 theorems. I'm just going to give you a big list. I will hopefully get through at least 9 of them. I think the 10th is maybe pie in the sky, but I'm hopeful that I'll at least touch on it. And the first 5 are really set in the general setting of competitive TLNs. And the second 5 are focused on a subclass, which we call combinatorial threshold linear networks, where we have much tighter control over what happens in relation to an underlying graph. So before I forget, I want to thank my many collaborators on this. First and foremost, Katie Morrison, up here at the top left. She is everywhere, so I'm actually not going to show her picture on different slides because her picture would be basically on every slide. For the other ones, Caitlin, Chris, Josh, Juliana, Caitlin, Vladimir, Anda, and Jesse, I will hopefully I've remembered to put their pictures on work that they participated in and contributed substantially to. Caitlin is a former graduate student of mine who's now an assistant professor at Keene State. Josh, Juliana, and Caitlin are current grad students. Chris and Jesse were former postdocs who were, worked a lot on this, for a couple of years each. Chris is now in Tatiana Engel's lab at Cold Spring Harbor, and Jesse is an assistant professor somewhere in the Bay Area. I forget the school. And then Vladimir is at Penn State, and Anda Dejeratu is at Stuttgart in Germany. So she's a mathematician. All right. I also want to thank my Women in Computational Topology group. So this is actually a group of applied algebraic topology, mostly postdocs and a grad student. And we started this project that led to Theorem 10 2 summers ago in a nice workshop in Australia that then really sparked a collaboration that ended up spanning a couple of years now. I don't have pictures for all of them because there are too many. Okay, so let's get started. The first thing I want to impress upon you is a kind of a geometric picture for how to think about threshold linear networks. It's been really useful for us. So we think of TLNs as this patchwork of linear systems. And one sort of useful way to break it down is to think about the individual equations as having these sort of two regimes, right, on either side of this nonlinearity. And so when this yi term is 0, that's when you flip. But these yi's actually define hyperplanes. And so in fact, there's a hyperplane arrangement that is exactly defining the TLN. The theta moves the hyperplane, shifts it back and forth, whereas the rows of the W matrix, W1J, W2J, and so on, are normal vectors giving the angle at which the hyperplane is oriented. And one of the things that's immediate when you think about this as in every chamber of the arrangement, you have a linear system, it's immediately clear that you're gonna have at most one fixed point per chamber. And so there's actually a one-to-one correspondence between the fixed points and the allowed supports of the fixed points. And this allows us to effectively label the fixed points purely based on who who the support is. The support being the neurons that are active at the fixed point. The other ones outside the support are 0. Okay, so here's a picture for a simple n = 3 network. This is the hyperplane arrangement. You can see there are 8 chambers here. Only one of the chambers actually contains the fixed point corresponding to the linear system. And so the entire game is to figure out in each chamber who is the fixed point. Does it live in the chamber where that linear system is actually governing the dynamics? And if so, then it becomes a fixed point of the full TLN. So it's a complicated picture, and it's not immediately obvious that you should be able to find simple rules figuring out who are the fixed points of the network from this picture. Okay, so basic assumptions that we make about TLNs for purposes of the proof. So we loosen these assumptions sometimes when we do modeling and simulation because a lot of the behavior actually generalizes beyond that. But for purposes of proofs, we need things a bit stronger. So the first one is we assume the TLNs are competitive, meaning the W entries are negative or 0. And we also assume, because otherwise the activity would die, that these B's, the external drives to the individual neurons, are non-negative. And we also have a non-degeneracy condition. So if you think about the hyperplane arrangement, this actually guarantees that the hyperplanes intersect in some generic way, that you don't have these fine-tuned problems. And one of the ways we guarantee that is by having certain determinants forcing them to be non-zero. This is actually because determinant being 0 is such a fine-tuned condition. Satisfying the non-degeneracy is actually very, very easy, and the degenerate TLNs are a set of measures 0 in the space of all TLNs. So this really is the typical scenario, but you have to watch out sometimes if you choose parameters yourself that you might end up in a degenerate case. Okay, now some quick facts. So I've already mentioned you can label the fixed points based on their supports. Once you know the support, you can work out the fixed points. So the entire game of figuring out fixed points of these networks is figuring out which subsets of neurons can support a fixed point. They typically have multiple fixed points, stable and unstable, at most one per support. A fixed point is stable if and only if this matrix, the sub sigma, means I'm restricting now to rows and columns indexed by sigma, which is a given support. A fixed point with support sigma is stable if and only if this is a stable matrix, meaning all eigenvalues have negative real part. Every fixed point has at least one eigenvalue with negative real part, by the way. So there are no sources so to speak, among the fixed points. And that means that every fixed point, even if it's unstable, does have a stable direction pointing into it. Now, this is really important. It's a simple application of the Perron-Frobenius theorem. It's easy to see, but it's really important because it means these fixed points have an outsized role in shaping the dynamics, even the unstable ones, because you do still go near them, even if they're unstable. We also have this important fact that fixed points are preserved under restriction to their induced subnetwork. So if you have a fixed point and then you look at the induced subnetwork where I'm restricting W and B, of course, only to entries in that support, then it should also be a fixed point in the subnetwork. But the converse is not true. You can have fixed points of the subnetwork that disappear when you embed the subnetwork in the larger network. Okay, so now let's get to the first of my theorems. The first one is kind of a general theorem about where the activity goes coarsely. So it turns out that you can think about the nullclines. The nullclines of the TLN are also given by a hyperplane arrangement. The hyperplane arrangement consists of hyperplanes for this entire quantity being 0. This is xi dot. Okay, so that's natural for the nullcline. Glued together, so one of those, that's like this diagonal red guy, glued together with xi equals 0 once it hits the axis. So the nullcline is actually this piecewise linear thing. So it's two hyperplanes glued together at this point. There's another nullcline for n2, and this is the general picture in all n. So this nullcline arrangement actually, it's different from the arrangement I showed you before, but it's closely related. This partitions your state space. See here I have x1, x2, but of course you should think of this as a general picture for all n. It partitions it into chambers where you can put a sign pattern in each chamber that tells you which neurons are going up and which neurons are going down. Okay, which derivatives are positive and which are negative in each chamber. And so here you see you get all 4 possibilities. And there are some chambers that are pure minus, others that are pure plus. The one that contains the origin is always pure plus. The far one that kind of goes out to infinity is always pure minus. And the theorem says that if you look at the union of the mixed sign chambers, the ones that have at least 1 plus and 1 minus, that the activity always gets sucked into that union. That's what the theorem is telling us. Apologize, my phone is ringing. Okay, and so this is actually pretty interesting. So what it tells us is that, no matter what your arrangement is, so here are the three different qualitatively different nullcline arrangements you can have in n equals 2, but of course the theorem is for all n. No matter what your arrangement is, your activity, wherever you start, is going to get sucked into the shaded region. Okay, and so looking kind of at a larger network, what does this mean? It actually puts some bounds on the total population activity, because the shaded region, if you look at it, it's sort of in this narrowish band. Okay, and so if you think about the standard simplex where the total population activity is constant, right, this is kind of like a weird fattening of that. And so what happens is your total population activity for any given network will initially kind of shoot up or shoot down, depending on which side you start on, until you get into that union of mixed sign chambers, and then it'll stay relatively stable even as your network transitions. And here in this network, you have these spontaneous transitions, different neurons are firing at different times, but you get into that union of mixed sign null chambers and you have this relatively stable population activity. So that's kind of nice because it gives us, it's not a balanced network by the proper definition of balanced network, but there is some sense in which you have this bounded activity where even if you have kind of large transitions on individual neurons in terms of how active they are, the total population activity is relatively constant. Okay, so let me move on to the next pair of theorems. So theorem 2 is about index and parity. So one funny thing that Katie and I noticed early on when we really started studying these networks for stable and unstable fixed points is that there was always an odd number of stable fixed points. No matter what example we try, the total number of fixed points was always odd. And we mentioned this to Vladimir. And because he's a differential geometer by training, he immediately thought, there must be an index theorem. And in fact, very quickly, he found that as a simple application of the Poincare-Huff theorem, that's the hairy ball theorem, for those of you who've heard of that, applied in this context, we get the following theorem, that if you define the index of a fixed point support, right, or a fixed point based on its support, to be the sign of the determinant of this matrix, I minus the restricted W, then the sum of all those indices across all the fixed points must equal 1. And of course, this index, given our non-degeneracy conditions, can only be plus or minus 1. And so in particular, the total number of fixed points has to be odd because you have to have one more plus 1 than a minus 1. You can't get a 0 here. And so this immediately gave us that result that this is always true, the odd number of fixed points, of course, in the non-degenerate case. And as an immediate consequence, we can also see a bound on the stable fixed points. Since they all have index 1, which is sort of easy to see by the definition, you can have at most 2 to the n minus 1 of them. And for those of you who've seen me talk about core motif fixed points in the past, those are also all index 1. Okay, next theorem. I'm going to go through some of these kind of quickly. This one is very technical. It's a sign conditions theorem, and I only put it up here. I'm going to flash it very quickly, but I want to, it's coming from a paper that Katie and I wrote with Jesse Genison, our postdoc, and it really has allowed us to prove a lot of other theorems that maybe are superficially more meaningful. So this one actually gives us a characterization of the fixed points of a TLN in terms of various signs of certain determinants that come from Cramer's rule. Okay, so this is a technical one. I go through it quickly, but it's going to be used heavily in the proof of the next theorem. Okay, so theorems 4 and 5 are about these different regimes for general competitive TLNs. So fixed point regimes. So I want to start with this idea of the graph of a TLN. So one of the tools that has been really important for us is to be able to associate a graph to one of these networks. So given one of these W matrices, we can associate a graph as follows. We simply check if the Wij is bigger than -1, then we put an edge from j to I. And if it's less than -1, we don't, or less than or equal to -1, we don't. And the -1, by the way, is the coefficient of the leak term, the negative xi. So really what we're doing here is we are checking whether the interaction is stronger or weaker than the neuron's own self-inhibition through its leak term. Okay, and the question is, how much does this graph tell us about the dynamics and about the fixed points in particular? So up to n equal 2, this graph actually tells us everything. It fully classifies the different fixed point regimes that our network can be in. So if you look at all the, the competitive W matrices for n equal 2, the graph can either be an independent set, a click, or a single edge. And that actually corresponds to the 3 qualitatively different null-Klein arrangements that you can have. And so it's no surprise, given that fixed points are intersections of null-Kleins. You can see here the 3 fixed points here, 1 fixed point here, 1 fixed point here. It's no surprise then that the graph, because it fully determines the null-Klein arrangement, qualitatively, it's going to give us all the fixed points. But for larger n, it's not so clear. There can be multiple dynamic regimes per graph. And here's one of the ways that you can see this. So if you look at, say, this graph, here's a matrix that is consistent with it. So if I take this W matrix and compute the graph, I will get exactly this graph on n equal 4 neurons. And it has different for different initial conditions, it will go into different attractors. So for some initial conditions, it'll go into this nice 3-cycle attractor where 1 goes to 2 goes to 3. So here's our sort of our first limit cycle that you see. For a different initial condition, it'll go into a stable fixed point supported on node 4. And you can see these attractors reflected in the fixed points. So there's a fixed point supported on 1, 2, 3. That corresponds to this attractor, meaning if you initialize near it, you will fall into this attractor. There's one supported on 4 for the stable fixed point. And then there's a third fixed point. Remember, we have to have a total number that is odd that serves as a kind of tipping point. It's on the boundary of the basins of attraction. And you can see that better in the state space picture. So here's the 1, 2, 3, 4. And perturbations around that either get sucked in to the 1, 2, 3 limit cycle or get sucked into the 4 fixed point. However, this same graph actually has a different dynamic regime where there's only one attractor, where only that stable fixed point for node 4 survives. And you can see that reflected in the change in the fixed point supports. So for the first W matrix, you have the 3 fixed points reflecting the 2 attractors and the tipping point. For the second W matrix, you only have a single fixed point, and it reflects the survival only of that one stable fixed point attractor. And so classifying the different regimes, the different patterns of fixed point supports that you can have, give you a window into the different dynamic regimes that one of these networks can have based on the graph. So Chris Langdon, when he was a postdoc with us, he sort of ran with this idea together with this, the previous theorem 3 on the SIs, and he started classifying what are the possibilities for the different dynamic regimes given the graph. And for n equals 3, he used the theory of oriented matroids, which is sort of a fancy combinatorial theory in mathematics, and he was able to use that to sort of classify what are all the different ways in which those null lines can intersect as you vary the W matrix. And so he found, for instance, for this graph, that you have exactly 4 different dynamic regimes. There's an odd number of fixed points in each one, but basically these are the 4 possibilities for what the fixed points can be. And he even was able to understand bifurcation parameters. So in other words, these differences between synaptic weights move you from one dynamic regime to another. So if you're thinking about, training a very simple network like this to do some dynamic tasks, this actually tells you what are all the possible fixed point regimes you can go into and how you can move between them by adjusting the weights. And so, we have this ambitious goal to try to do this for all, initially for all n equal 3 graphs. And so there are 16 graphs on 3 nodes, and he was able to use this oriented matrix theory, really understand the combinatorics, the combinatorial geometry, and classify the fixed point regimes for all 16 of these graphs. Now, there's one interesting thing that happens, and this is our next theorem. Okay, so this is theorem 4, is basically this figure, right? The theorem is that these graphs shown below really are all the fixed point regimes for each one of the networks. Okay, interestingly, you'll see at the bottom, there are some networks that only have a single fixed point regime. And they only have a single fixed point in them as well. Okay, so these are like boring graphs where no matter how you change the W matrix, provided the W matrix gives you this graph, remember the graph is just checking which entries are above -1, which entries are below -1. So there's a huge infinite, uncountable family of W matrices, of course, for each one of these graphs. But no matter how you wiggle it, you are going to be stuck with a single fixed point supported on, either node 3 in this case, nodes 1, 2, and 3 in this case, and so on. And so we call these robust motifs because they are the qualitative dynamics, so to speak, are invariant to changing the weights. The fixed point itself will move its location, but its support will stay the same, and qualitatively the dynamics we expect to stay the same. So so this was very interesting for us to think about these robust motifs. And one of the questions we asked is, what are they for larger n? And we were very surprised to be able to do this, but we were actually able to classify all the robust motifs for all n. Okay, so in fact, they come in, other than the 2 exceptional ones we've seen before, the independent set of size 2 and the 3 cycle, which are robust, the rest all come in one of 2 infinite families that essentially consist of a directed acyclic graph, so completely feed-forward network with a target node, or with a target node that's part of a clique. Okay, so I'll show you the first few of these, but this construction, of course, can be arbitrarily large for all n. And so these are all the robust motifs up to size n equal 4. You can see the size 3 ones that we've already looked at. And basically this is everything. So what does that mean? Well, if you have these motifs, again, no matter what the plasticity rule you have on the W matrix, provided you stay with the same graph, right? If you of course change graph, that changes things. But if you stay within the same graph, there will be no change to the fixed point, to the combinatorics of the fixed point supports, right? So the fixed points may move around, but the number of fixed points and who they're supported on will stay exactly the same. For any other graph, there are at least 2 dynamic regimes. So that means that you do have flexibility on the vast majority of graphs, that there may be multiple dynamic regimes depending on how you change the W matrix. And here's a quick count. The number of directed graphs explode as you go up in n. For n equals 6, it's already 1.5 million non-isomorphic directed graphs. The number of robust motifs also increases sharply, but at a slower rate than the number of graphs. So this, this is a vanishingly small fraction of the total number of graphs, but they are very easy to construct. They're essentially these feed-forward networks, and having these in a network probably provides some level of of robustness to perturbing the W weights. So we find that interesting, and there's sort of ongoing work following up with that. Okay, now I want to, about halfway through, I want to switch gears and do a little interlude. I'm going to switch to the subclass of combinatorial threshold linear networks. They are all special cases of TLNs, but they're ones where the W matrix is constructed from the graph rather than the other way around. So there are fewer parameters to play with. So let me just quickly tell you about CTLNs. So it's the same TLN dynamics, but instead of allowing different B values, we have a fixed theta drive to all the neurons, because we really want to see what's the effect of the graph, what's the internally generated dynamics. And so we don't want to allow that to be different across different neurons. So we don't want to inherit dynamics from the stimulus, so to speak. And the key thing is that you start with a directed graph, and the graph fully determines the matrix. So when there's an edge from J to I, you give a value that's above -1. So this epsilon and delta are positive. When there's not an edge, you give a value of interaction that's less than -1. So what you're doing is you're really rigging a network so that its graph will be the graph that you started with. But you're only allowing two values for the synaptic weights. So one value above -1 and one value below -1. And there's a technical condition here where we want epsilon to actually be less than delta over delta plus 1. So in particular, that means it's less than 0. And that's consistent with the idea that these should be competitive, inhibitory networks, effectively inhibitory networks. Now, we think of these as coming from a bunch of excitatory neurons and a sea of inhibition, I should say that. That's sort of the story that we think about. And so the idea is that when you have a connection in the graph, say node blue inhibits the red node, but less than it would inhibit itself through its own self-leak term. So we think of that as a combination of having an excitatory connection together with indirect inhibition. So there's like kind of a global inhibition that happens that gets added on to excitation for the -1 plus epsilon, and then the -1 minus delta is just that strong global inhibition. So the graph is encoding this pattern of weak and strong inhibition. And so you can think of it as a generalized winner-take-all network. And for fixed parameters, right, so if you fix delta, epsilon, and theta, only the graph can change between different networks. And so when you see different dynamics, it really is due to the differences in the connectivity. So it's really a way to isolate the role of the graph, the role of the connectivity. So let me just show you some fun examples. Here's a very simple graph. We call this the 5-star, and it's cyclically symmetric, and it produces a limit cycle you would expect where the neurons go in order 1, 2, 3, 4, 5. However, for a different initial condition, same graph, same W matrix, same everything, just changing the initial condition, you can get a completely different looking attractor, which I think looks really fun. It's like the curves look like they're melting. So we call this the Gaudí attractor because it reminds me of the famous architect from Barcelona. So you get rich dynamics, even in very simple cases. Here's a network of 9 nodes that has 4 different attractors. And we like to show this example because it shows how different types of attractors can coexist. So it's not like there's a fixed point regime and then a chaotic regime. You can have fixed points, limit cycles, and chaotic attractors. These are like strange attractors, all coexisting on the same network. The only difference between these solutions is the initial conditions that I've chosen. So again, same network, same W matrix, nothing changes except for the initial conditions. So they all have their own basins of attraction. So these are fun networks, and we can prove more about how to tie the graph of these networks to the dynamics. So the first theorem, this is kind of the oldest one in this vein, was proven with Vladimir and Ando a long time ago. And that is, if you have an oriented graph with no sinks, then the network has no stable fixed points, but bounded activity. This is kind of an important theorem for us to be able to explore interesting dynamics. If you just make random networks, you will have a bunch of stable fixed points, and you'll get sucked into those, and you won't see the cool limit cycles and chaotic attractors and so on. And so we wanted to rule that out, and it turns out that you can do it very simply. This actually relies on a fun linear algebra fact. The fact is that if you have a stable matrix, non-symmetric, but stable matrix, then every 2x2 submatrix also has to be stable. Of course, we're in the setup where the entries are non-negative, and we have the special diagonal But for the matrices that appear in our TLNs, this nice fact allows us to rule out stable fixed points, basically by ruling out 2x2 matrices that are stable. This theorem, actually, I've put it in the CTLN section, but it also generalizes to the previous competitive TLNs with an additional condition on the W matrix. So I'll just make you aware of that. Okay, and so here's just kind of a random simulation. You take a random oriented graph with no sinks. So oriented means there's no double edges in the graph, and you're guaranteed no stable fixed points. So fun things will happen. You'll get interesting activity. Okay, next theorem is the one that has a lot of applications, the uniform integree theorem. So there are special graphs that have uniform integree, meaning every node has the same number of edges coming into it. So this one is, the cycles are uniform in degree 1, independent sets are uniform in degree 0, cliques are uniform in degree k-1, where k is the number of nodes, and so on. But they don't have to be symmetric. This, what we call a tadpole graph, is also uniform in degree 1. And the theorem says that no matter how you choose epsilon and delta to make these CTLNs, if G sub sigma is an induced subgraph of uniform in degree D, then sigma, right, those are the neurons you're restricting to, that's the support of a fixed point in the full network G, if and only if there's no node outside of the subgraph that receives D plus 1 or more edges from sigma. Okay, again, this is independent of epsilon and delta, and this theorem gives us a lot of power to understand what's happening at the level of the fixed points. So a corollary for a cycle, which is uniform in degree 1, you have a fixed point corresponding to it that survives in the larger network if and only if no node outside of that cycle receives 2 or more edges from the cycle. So in particular, if you look at a graph like this, I have 2 3 cycles here, 1 4 5 and 2 3 5, and 1 4 5 has a node external to it, node 2, that receives 2 edges from the cycle. You see that? And so that fixed point does not survive, whereas 2 3 5 does not have that property. And so this is an if and only if, so I know I have a fixed point for 2 3 5, and I know I do not for 1 4 5 in the context of this larger network. And corresponding to this, one of the reasons, again, that we're so interested in fixed points is that we get limit cycles corresponding to these graphs like cycles when the fixed point survives. And so here you get a limit cycle for 2 3 5, but not for 1 4 5. There's also a nice corollary for cliques. For cliques, the fixed point is going to survive if and only if no node outside receives k or more edges from G, where k is the size of the clique. So how many of these, surviving fixed points for limits for cycles and cliques do we expect in large random graphs? So it turns out, because of this rule, because of this nice simple rule, we can actually compute expected values for the number of k-clique fixed points and the number of k-cycle fixed points. And we get these formulas where P is the Erdos-Randi probability, N is the number of nodes, and K is the size of the clique or of the cycle. And here are some plots that show you what these things look like. So cliques, cliques of different sizes peak at different values for P. This is for 100 nodes, 170 nodes. It's actually we have to sort of figure out how to approximate this formula to actually get the computations for larger N. For cycles, you see that the larger the cycle is, the peak is coming sooner and sooner in P. So this is P around 0.05 is right here. And so if you have a high connection probability, you will see a drop in the surviving cycles. So basically what happens is more connections create more cycles, but they also kill more because you have those outgoing edges that are gonna mean there's no fixed point associated to them. All right, so let me get into some applications of this theorem. So the first is a neural integrator. So one of the kinds of networks that tends to be useful to model certain phenomena is an integrator where you keep track of how many pulses the system has been hit with as a function of the state of the network. So this is a simple, what I call a TLN counter. So I have 2 cliques and they have these edges going forward. But notice the 2 cliques are surviving because no node is getting 2 edges from a 2 clique. Each of these nodes is getting at most 1 edge. So by the theorem, every one of these 2 clicks produces a stable fixed point. But when I give a pulse to all the nodes, there is this bias here. And so what happens is I slide over. So if you can see down here, this is a pulse train. These are pulses. That just means I increase theta, the theta parameter in the equations, right? The external drive for all the neurons. So you can see that gray band, all the neurons are getting hit equally. And what happens is you have hysteresis in the network and the fixed point slides over to the next click. And so I hit a second pulse, I slide over again. Third pulse, I slide over again. And I keep going. And this is, of course, periodic. And so then I wrap around. All right, so what's happening here is this network is really counting the number of pulses. Whichever fixed point you're in is telling you how many pulses have transpired since the beginning. We can also do a sign counter. So in the previous one, the edges were going the same way for the top row and for the bottom row. Here, the edges are going right in the top row, and then I have this leftward bias on the bottom row. So now if my pulses, I can have right pulses and left pulses. The right pulses only stimulate the top row, and the left pulses only stimulate the bottom row. So here I'm showing a pulse train with left pulses in blue. Sorry, right pulses are the top row in blue and left pulses in red. And you can see here that the activity now remembers the difference between the left and the right pulses because you're moving left and right. And you can also even know which direction you came from based on, well, maybe another, there's a version of this where you can even remember which direction you came from. Okay, so this is again, something that will count left versus right pulses. It's very simple, right? So I show you this not because it's hard, I show you because it's easy to just construct networks like this once we understand the fixed point structure. And then finally, this one's just for fun. This is if you get rid of the bottom edges altogether and you just have these dangling 2 clicks coming off of a cycle, this produces a kind of roulette wheel. So stimulating the neurons in the cycle will, no pulses this time, just one initial condition. It'll cause the activity to spin around some unknown number of times, and then eventually stabilize on one of those clicks because they are all stable fixed points. So we call this the roulette. Okay, so in this vein, we don't have to use clicks. We can also use limit cycles for individual components. So again, using the theorem, I can construct a network like this where I put a bunch of these 5-star modules, glue them together. And this is, kind of like a continuous attractor network, except instead of having a bunch of stable fixed points that are all sort of overlapping and adjacent, I have a bunch of limit cycles. And they do have overlapping neurons, right? Like neurons 4 and 5 belong to 2 different limit cycle modules. And so you can see on their own, all of these are stable. The theorem actually tells me that there's not enough outgoing edges to any node to lose any of those fixed points. And so I expect the limit cycles to be there for each one of these components. And I can stimulate, say, node 3 to start in the first limit cycle, then node 6 to move over, node 9 to move over, and so on. And so with different stimulations, I can move things over. But even beyond that, I can actually stimulate all of those red nodes every time. So again, just do a global pulse, right? In the sense that it's hitting every one of those attractors, and it will just slide me over by 1 each time. So this is also an integrator, right? Or something that's keeping track of position. And the nice thing about this is it's really this like global signal. The signal does not carry information about what specific attractor you should go into because it's hitting them all equally, right? It's hitting all the red nodes. But depending on where you were, you're sliding over to the next one. Okay, so I like to think of this as something that, is a kind of mechanism maybe we want to think about when we think about, hippocampal phase precession and, bump attractor networks and so on. These aren't the classic bump attractors because they're not fixed points, they're limit cycles, but you can still have this nice way of moving them without a specific cue, right? It just kind of, again, integrates pulses. And just to see how fine-tuned this is not systematic by any means, but we added some like 2% noise to the weight matrix. So just making the synapses not so perfect, right? Because I'm making this in a CTLN, so the synapses are binary. Now I'm kind of screwing them up a little bit so they're not all identical. And you can see, here I get a failure of transition, maybe I need a stronger kick to make it work, but still it more or less continues to work. So it's fairly robust. It doesn't need fine-tuned synapses for this to work. Okay, so I'm gonna, in the interest of time, I think I'm going to very quickly skip over graphical domination. So this is a particular, again, this is a technical theorem. And I'm including it here because it is so important, all right? So it's telling you properties of a pair of nodes in a graph. So if I have a node K, I say graphically dominates node J, basically if it's getting all the inputs that J is getting and more. That's the classic inside-in domination. We also have these other variants, outside in and inside out. And the theorem is that when you have these domination relationships, it tells you a lot about fixed points. So a given fixed point support, for example, cannot have a pair of nodes where one dominates the other. So fixed point supports have to be sort of egalitarian enough, okay? You really can't have a node dominating another within a fixed point support. And so that's kind of the essence of the theorem. And again, I include this for completeness because it is really central to a lot of the things we can prove about CTLNs. In particular, it tells us that there are no fixed point supports that contain proper sources, meaning nodes that have only edges going out and no edges going in. Feed forward graphs cannot be fixed point supports because they have these source-like terms. Subgraphs with targets, these are kind of nodes that receive from the rest of the graph, cannot support fixed points, and so on. So it really allows us to rule out a lot of graphical structures. We can just say immediately from the graph, this cannot support a fixed point because you have some domination problem. Okay, so now let me get to this. I think this is the last theorem that I will talk about, is the cyclic unions. So this one, I think the fact was first discovered by Caitlin, my former graduate student, when she was doing her thesis. And then we were able to prove it in a very general way. But this is a way of making new networks from old ones, gluing together smaller networks to make larger networks and still maintaining control over the fixed points. So a cyclic union is a graph with n components, capital N, tau 1 through tau n, where they're cycled together like this, so that from tau 1 to tau 2, you have all the possible edges. Every node in tau 1 has a forward edge to every node in tau 2, but nothing going backwards, okay? And so you connect them all in this chain, and here's the remarkable fact. These taus can be whatever subgraph. G restricted to tau sub I here is the subgraph. Fp of G restricted to tau I are the fixed points of the subgraph. And if you know the fixed points of the individual component subgraphs, then you know the fixed points of the entire network. It's quite remarkable when you remember, the no-Klein arrangement, the business with the chambers, and how complicated it was to figure out what fixed points survived the full network and so on. This is actually, I think, quite remarkable that you can figure out the fixed points. You know exactly, this is an if and only if statement. Sigma is a fixed point of the full network, if and only if it restricts. So sigma sub I is the restriction, sigma intersect tau sub I, restriction to one of those components, if and only if it restricts to a fixed point of a G sub tau sub I for all the tau sub I's. Okay. So just to give you an example, so focus here on the left, here is a cyclic union of 4 different graphs. These individual graphs we can analyze, they're small, we know they're fixed points. Down here at the bottom, you see what are the fixed points of tau 1. It's 1, 2, 3, and 1, 2, 3, this little graph, okay? And so each one of those little graphs we have, through other analysis using domination and the uniform integree result, we can figure out the fixed points. And now we have the fixed points for the entire network by gluing those together, right? So it's really a mix and match. I take one from each component, and I can make the product of these sizes fixed points. So I have 3 times 1 times 3 times 1. There should be 9 possible fixed points, and that's exactly what we get. Okay, so we have this tremendous control in the cyclic union of who the fixed points are given the fixed points of the component graphs. And this, I'll skip over this. This is just some count how many fixed points. One of the applications of the cyclic union is to create networks that have lots and lots of limit cycles. But I'm going to end with an application to central pattern generator networks, because I think this is pretty new and quite fun. So Juliana, who's a current graduate student of mine, This kind of emerged from a class project initially, where she learned about central pattern generators and different models for them. And, you know, for those of you who, just to jog your memory, you know, a quadruped, right, an animal with 4 legs, has different gaits. So here are some examples: walk, trot, gallop, bound. I just took these from kind of a recent article, I think is in robotics, that uses coupled oscillators. Okay, so there are lots of coupled oscillator models. Bart Ehrmantraut, Nancy Capel, many others. Marty Golubitsky has also studied central pattern generators for symmetry. There's a long tradition, and I'm not going to do it justice in terms of the history right now, but you know, lots of people try to come up with small networks that will get these different locomotive gaits. Okay, so we actually tried to go for 5 different ones: walk, trot, the gallop, bound, pace, and pronk. And the strategy, so here are like these, the red, blue, green, these colored neurons, red, blue, green, and brown, those correspond to the different legs: left front leg, right front leg, left hind or left back leg, and right hind / right back leg. And the strategy was to use cyclic unions, okay? So we made these, you know, we constructed a graph that had clicks between the different pairs of legs that needed to be synchronized for at least one gait. And then for individual gaits, we made these cyclic union motifs. So Juliana played with this for a while and, you know, found that she could make bound very easily by adding these auxiliary nodes that would switch you between. And this is a perfect cyclic union now. This is now pace. Now we're grouping together different pairs of nodes. This is trot. So trot is interesting because it takes diagonal legs and synchronizes them and then alternates between those. Walk actually does one leg at a time. So here we need kind of 4 auxiliary nodes to move between. But these are all cyclic unions, okay? So graphically, these are all very simple. And finally, pronk, which is where they're all the legs go up and down together, okay? And so individually, she got them all to work. So if you look at the activity down here, I don't know if you can see in the pink, the first 4 nodes are the ones corresponding to the legs, and the others are the additional nodes in the network, so you can see. And down here, we're only showing the ones in the legs in color, okay? So you can see these different ones. Now here's the magic, okay? We were able to just glue these all together. This is literally the union of all 5 of those cyclic unions. Okay, just fused together. We just kind of matched up the common nodes corresponding to the legs, and then just included all the edges. Okay, so this is, you know, a priori it's a mess. It has 24 nodes. This is the G graph. It's a mess, but it was very simple to construct, right? Because each gate individually made a lot of sense, and then we just kind of glued them all together. And then we picked some epsilon delta parameters, okay, and checked, can this network, this super network that has all the different cyclic unions in it, can that actually still produce all those individual gates, okay? And the answer is yes. Every single one of those gates, in fact, these pictures that I've been showing you, although of course on the individual gates we've checked that they're identical, these pictures all come from the super network, in fact, okay? So between these different gates, there are no changes in parameters. There are no change, you know, nothing is changing in the network. The only thing that changes is the initial conditions. And the initial conditions aren't hard to find either, because you just have to initialize on one of these auxiliary nodes that is specific to the gate. So here I initialize on node 13, here I initialize on node 15, here on node 17, and so on, and it goes into the appropriate pattern. And if you don't believe me, here's a network. Here's a single simulation where I've initialized on bound. So you can see the nice bound gate here. And then I give a kick to the node 15. And that kicks me into pace. And then I give a kick to node 19, which is one of the walk nodes, auxiliary nodes. And that kicks me into walk. And then a kick to 23 takes me to pronk. A kick to 17 takes me to trot, and so on. So these are just little kicks. This is the same simulation. W doesn't change. You know, and theta changes only at these kicks. And so what happens at the kick, theta continues constant for every node in the network, but it goes twice as high just for node 15, just for, a few milliseconds of time. And here node 19 and so on. And otherwise it's the same network. So in between here, it's exactly the same network. The kick has just taken us to a different basin of attraction. So we've fallen into a different attractor. And again, if you're worried about noise, we added 1% noise to the W matrix here to see how fine-tuned this was. And the kicks all still transitioned you very nicely. The dynamics were basically the same. 5% noise, and I got a transition failure. Of course, again, the kick, maybe I need to make it stronger, and maybe I would still transition. But the point is, when I added more noise, I did see some effect here. But overall, the network seems pretty robust. So we made it in a CTLN, but it need not be a CTLN. So the philosophy is, if you can do it in a CTLN, you can do it in a more general TLN. And then, of course, you should be able to do it in other networks as well. So this is really kind of a proof of principle that you can have, these 5 coexisting gates. No synapses have to change. No parameters have to change. They really coexist, and just different initial conditions, or kicks, which take you to different parts of the state space, will transition you between them. Okay, so I think it is almost noon, so I am not going to get through this last one, but here's I'll just say a few words about this last theorem. This is the one that really has a little bit of an algebraic topology flavor to it, because what it's based on is this idea of covering a network with directional graphs. And so I don't have time to really get into the details of this, but directional graphs are these graphs where your fixed points are sort of concentrated on a subnetwork. And so what happens, the sort of heuristic, is that the activity likes to flow to the subnetwork where the fixed points live. And so you can use that intuition to sort of glue together directional graphs and construct sequential activity, even if you have back edges, right? So in this particular chain, I have edges going forward and backwards between different levels. But because I'm gluing together directional graphs, I'm actually guaranteed that the activity will flow forward, and it does. Okay, and so that's kind of a nice story in and of itself, the directional graphs, and it turns out you can sort of cover larger networks with directional graphs. And in the spirit of the classic nerve theorem from algebraic topology, we were able to prove theorems about the fixed points of the underlying graph based on the fixed points corresponding to the reduced graph, which is the nerve. Which is just sort of keeping track of how the directional graphs overlap with each other. Okay, and so this is a very nice. This is work with all these names. This is the Women in Computational Topology group that did this project. So I will just skip through these slides because I'm definitely out of time now. And that's it, all done. And just want to end with thanking again all of my collaborators over the years, also NSF and NIH grants that we were lucky enough to get. And that's it. Thank you.